Hello and welcome everybody to lecture video 6.2 on Kalman filtering. In this video we will introduce the basic linear Kalman filter, which is a very efficient implementation of the base filter that we looked at in the previous videos. So as you remember from the previous video, we introduced there the histogram filter to estimate the position of a robot in 2D. And the histogram filter did that by representing the state space using a grid. And every cell in this grid then indicates or stores the probability that the robot is located in this particular cell. Although this is very easy to understand and very easy to implement, it has several disadvantages. And the most striking disadvantage is that it's very inefficient. And the reason for that is that we need to discretize the state space, of course, and even in a two-dimensional world, we already need quite many cells to represent the state space. So even in 2D, with a reasonable resolution, you can end up quickly with maybe a grid of 100 by 100 or 1000 by 1000. And that needs lots of memory, of course, but also on the other hand, this needs lots of computation power then to update the whole grid. And this is still, while this is still feasible for 2D and actually occasionally still used by scientists and roboticists, it scales very poorly with higher dimensions. So imagine that you need to estimate 3 degrees of freedom, then the number of cells already grows cubically. And if you would like to estimate the state of a 6 DOF pose in 3D, then this grows extremely quickly. And the other problem is that if you want to have a reasonable resolution, say for example you want to know the position of the quadrotor up to a centimeter or so, then you need, even for a few meters already, hundreds and thousands of cells in every, along every dimension. So the question is, isn't there a way to represent the state more efficiently? And this is now where the Kalman filter comes in. The Kalman filter does that by representing the state in a different way, namely using normal distributions, which means that we have to store much less information, simply the mean and the covariance, to represent the state. And the second advantage is that because it represents the state using a continuous random variable, it doesn't have this discretization effect of the grid filter. So the interesting thing is that the Kalman filter has been developed and used for the first time in the late 50s. It was actually developed by the NASA in the Apollo program. So its first application already was aerial or space navigation to estimate the trajectory of the Apollo rockets. And the cool thing is, and this is also why it was applicable already in the 50s, is that it's super efficient because it requires only very few matrix operations and very few numbers, even if you have 6 degrees of freedom or 10 or so. And its applications today are very wide, so it's not only used in robotics and in space navigation, but also for as diverse things as economics and weather forecasting. Good. So at the basis of the Kalman filter, we have the normal distribution to represent the state. I guess most of you will have seen normal distributions before. Just to remind you a bit how this looks like, if we have a one-dimensional, first let's only look at one-dimensional normal distributions, which are also called univariate normal distributions. Imagine we have a random variable of which we say that it is normally distributed, then we write x tilde this kaleographic n. And the parameters of such a normal distributions then are its mean value and its variance. And this variance is, can also be written as the squared standard deviation, and the standard deviation is usually abbreviated with a lowercase sigma. And then we can specify a probability density function for that x takes a particular value. And this is then given by this exponential, negative exponential, which looks like this bell shape. And now it's interesting to note that the most likely spot always is at the mean of the normal distribution. And the further you go away, the less likely the values become. And just for having an intuitive feeling what this variance or covariance actually means is that within one standard deviation or around the mean, we already have 68% of the probability mass. And within 3 standard deviations around the mean, we already have 99% of the mass. We can extend this easily to multivariate normal distributions. I indicate this here again by bold capital letters. So this x here now has multiple dimensions, for example 2 or 3 or 6. And then of course also the mean vector needs to be a vector to specify the mean. And instead of having this simple variance, we now have a so-called covariance matrix. And then again, we can specify the probability density function, which looks almost exactly the same, just that we need to use this covariance matrix here and to invert it in the exponent. Good. And this is now a visualization of how this density looks like in 2D. So here we have a random variable which has two dimensions, x and y, and now the third dimensions again gives the set in the z direction gives the probability density at this location x and y. And you can see that it still has this bell shape, but now the covariance matrix actually can shape the appearance of this bell. So it can be symmetric and a nice round bell, but it can also be stretched in one direction, and it can be rotated. And therefore it also makes sense to look at the probability density function from above, because sometimes it's a bit hard to see how this covariance actually looks like in 3D. So if you would move the camera up and then look from the top onto your plot, you can visualize it, of course, with colors, but you can also visualize so-called isolines at a particular height. And then again, you can find heights that correspond to certain probability masses inside of them. For example, you can say that this red ellipse here has everything that's located inside of that has a mass of 68%, for example. But even more common is, of course, to have an isoline of 95% or 99%, for example. Good. Now, a few properties of normal distributions which are important later for the Kalman filter. So the first good news is that normal distributions behave linearly. So if we have one random variable x that is normally distributed with a mean of mu and covariance sigma, and we now define a random variable y that is a linear combination or of a matrix A times x plus some offset b, then we can directly move these coefficients into the normal distribution. So we know that then that this y is normally distributed again with a mean of r times mu plus b and a covariance of r times sigma times A transposed. And the other good news is that if you intersect two Gaussians, then you obtain again a Gaussian. So you can imagine this as follows. You have two random variables, x1 and x2, and both of them are normally distributed, but with different parameters. Then we can compute an intersection just by multiplying the two densities together. If you fill in the values, then you see immediately that the result has to be again a normal distribution. And the interesting thing is now to look at how the new mean and the new covariance is computed. And we can see that the new mean is essentially a weighted average between the old means weighted by the covariance. So essentially if say for example the second Gaussian here has a very large covariance, so it's very broad, it's very wide, uncertain distribution, while, say, for example, x1 is really narrow and has a very small covariance. So the random variable x1 has much less uncertainty than random variable x2. Then the result of the intersection will be strongly influenced by mu1, so by the first random variable, because sigma 2 is large. And sigma 1 is relatively small, so the influence of mu2 will be relatively limited. And then we can also compute a new covariance, essentially by adding the inverse of the individual covariances and taking then again the inverse of that. And this generally means that the uncertainty shrinks, so the covariance shrinks, which means that if you combine two Gaussians, then the result will be more certain than the individual will be narrower and more certain than the original covariances. And now let's look again at how we can define a process model and using these normal distributions. We had before this stochastic process, which is also called a Markov chain. So we have the state in the middle, which is now a vector, and we have controls U that influence the state, and we have sensor observations Z that we can compute given the state. Now our goal is to estimate the x here in the middle, the xt, from the previous state, the controls, and the observations that we make. So now the first idea, of course, is to represent the full state, which is also our belief, by a Gaussian. So we say that this random variable x is normally distributed with a certain mean, mu t, and covariance sigma t. And this state now evolves linearly over time for the moment. For the moment, we assume that we have a perfect linear relationship, which means that the new state is a linear combination of the old state. So we multiply a matrix A, a system matrix, which is also called, times the previous state and obtain the new state. But now, as I said, we of course also issue controls, and we furthermore assume now that these controls influence our state. So we have a second matrix B called the control matrix that says how this issued control is influencing our new state. Good. And then, of course, we always assume that there is some noise in our system, for example, because the quadrotor shakes slightly, or because there are other disturbances like wind that we cannot model well. But we and so we have to assume that there is a third term, epsilon, that is our noise, and this noise is again normally distributed around zero, so it's so-called zero mean noise with a covariance of Q. And this equation now describes how we model the evolution of our state. So the current state is a linear combination of the old state and our controls and some zero mean noise. And now we also want to find a sensor model that is linear. So we say that our sensor observation Zt depends on the current state and is multiplied with so-called observation matrix C. Yeah. And again, also for the noise, for the observations, we assume that they are noisy. And this noise is again Gaussian with zero mean. So we can write now that the following equation that describes our sensor model, that the observations depend on linearly depend on our previous state plus some zero mean noise delta. So to summarize this, the Kalman filter makes the following two model assumptions on this discrete time stochastic process. We assume that the state evolves linearly and is a combination of our previous state, the controls, and some system noise. And we assume that we have a linear sensor that depends, where the sensor observation set depends on the linearly on the previous state plus some noise. And important is again that we represent the current state x as a normal distribution, and we assume that the noise is normally distributed with zero mean. Good. So just to specify a few of these dimensions of the dimensions of these variables, we assume that the state comes from R n, so an n-dimensional space. We assume that the controls come from an L-dimensional space, and by no means L does not need to be the same as N. So for example, we could have a three-dimensional state or a five-dimensional state, but only a two-dimensional control. For example, if you have a car that is driving forward, then it has a, even in 2D, it would have 3 degrees of freedom. So the state would be three-dimensional for x, y, and phi. But we only have 2 degrees of freedom for controlling. This is then called an underactivated system, because we can only change the speed of driving, and we can change the angle of our steering wheel. And then we have observations which are k-dimensional, and again, these observations do not need to coincide with the dimensionality of our state or our controls. For example, we could have a three-dimensional state, but a two-dimensional observation from GPS, for example, from which we only get our x and y position. Good. And and then we have the process equation that we've seen before, and this matrix A, of course, then needs to be an n by n matrix. The matrix B that defines the influence of the controls onto the state is an n times L matrix, and our measurement equation, in the measurement equation we have this matrix C, which needs to be an n times K matrix. Good. And as we said, we assume that our belief is Gaussian, and in particular we have to make certain assumptions on our initial belief. So in the first time step, our prior belief on where the robot is, and it is of course a Gaussian, but we need to specify for that the mu 0 and sigma 0. And if we are uncertain about where the robot is in the beginning, then we could choose this mu arbitrarily, for example initialize it with 0, and then set the covariance to a very large matrix, which just means that we are extremely uncertain and that we always have a flat, almost have a flat distribution over the belief space. And then, given these properties that we've seen before of normal distributions, we can compute the next state, which is also a Gaussian, which is again a Gaussian distribution then, just because it evolves linearly, and we can make use of the linear linear property of normal distributions, and also the observations are Gaussian because they are similarly just a linear combination. And now we apply, if we apply this representation to the base filter, we end up with a very efficient algorithm. So just for reminding you of how the base filter looked like, this is what we had in the previous videos. The base filter keeps track of a belief distribution of the posterior at time step t over the state, and it consists of 2 steps. It first integrates over the motion u, and then it integrates the sensor observation set. So just to remind you how this looked like, and now we can fill in normal distributions here first in the first step. So our process model here is the first term, for which we can just fill in the normal distribution with the new mean and the new covariance. And we can fill in our previous belief, which is again just a normal distribution. So both of that actually directly become can be filled in as in closed form from the definition of the normal distribution. And then by multiplying this together, if you write this out, which is actually not too complicated to do, then you end up with a normal distribution again, fortunately. And this normal distribution then just has again a new mean and a new covariance that can be computed from the matrices A, B, and Q. And this new belief bar, as we call it, because it's just a temporary belief, is then represented again by a Gaussian with mu bar and sigma bar. And then we come to the second step of the base filter, where we need to apply the sensor model. This step looks as follows. So we have this normalization constant that we ignore for a moment. We fill in the normal distribution as we had it and our previous belief. And if you multiply these two together, so this is a bit more tricky to derive, you end up again with a normal distribution, which consists of a new mean and a new covariance. And now the new mean is essentially the old mean, or the mu bar, plus the k, a matrix K, which is called the Kalman gain, that we will look at it in a second, times our observation minus the predicted observation C mu bar. So it's important to realize here that what the Kalman filter actually is doing is it blends between our previous estimate mu bar and the discrepancy between our sensor observation and our prediction. And the degree to which we believe our sensor observation is determined by this Kalman gain here, this matrix K, which essentially depends on the ratio between different noise terms. So, for example, if our previous state, so the uncertainty that we have currently in our state is this sigma bar T. And the noise, or the covariance of our sensor observation is this R. So essentially it depends on the ratio between our uncertainty sigma and the uncertainty of our sensor observation R. So for example, if we increase our uncertainty of the state sigma, then this Kalman gain will get larger and we will put more weight onto our sensor observation, set t minus c mu. On the other hand, if our sensor noise goes up, so if this R gets larger, then because it gets inverted here, a larger R means a smaller Kalman gain. So the more noisy our sensor is, because it has a larger R, the smaller this Kalman gain will be, so the less we will trust our sensor reading, and the more we will just stick to our prediction from the model mu bar. But nevertheless, in the end, we obtain again a normal distribution with a new mean mu and a new covariance sigma. So just to summarize now the equations of the Kalman filter, we have again, like in the base filter, the two steps of applying a sensor, the motion model and the sensor model. Now in case of the Kalman filter, the first step where we apply the motion model is also called the prediction step, because we make a prediction of our current state given the controls and the normal evolution of our system. And yeah, and the second step is also called the correction step, because we correct the estimate of our current pose given the sensor observation. And yeah, one important aspect to note here, again, as with the base filter, actually, is that the prediction step and the correction step don't have to come alternately. So you could have 5 prediction steps, for example, because you're getting the odometry at a much higher frame rate, and then 1 correction step when you're getting a visual observation. So these 2 steps can be executed in any arbitrary order, depending on yeah, what your sensors give you. The Kalman filter by itself is, of course, there's of course more to say about this. In particular, I have omitted all the intermediate steps in the derivation, but in case that you're interested in looking at the derivations, which are actually not too complicated to understand, it's something that you can really do by hand, by yourself, then I would recommend to look at the probabilistic robotics book of Troon, Fox and Bulgard. And in chapter 3 there is the full derivation of the Kalman filter containing all intermediate steps that you have to do. Good. So the good news now on the Kalman filter is that it's extremely efficient. So it is polynomial in the measurement dimensionality and the state dimensionality. The only costly thing that we have to do is to invert let's look here. We need to invert this expression here, which depends on the size of our observations and the size of our state. But everything else is just a multiplication of matrices, which is extremely fast to compute. And the other good thing is that it can be shown that this is actually the optimal solution. So it's the best estimate that you can get if you have linear Gaussian systems and a linear Gaussian sensor. This is a good approximation actually in most cases. Of course, there are situations where it's not a good approximation, but in most cases it is. The only problem is that most robotic systems actually are, of course, nonlinear, right? So it's hard to specify this very simple linear transformation matrix for the state or for the sensor. But and now let's look at how to deal with that nevertheless. So if we have now a nonlinear function, so instead of having this linear dependency between the previous state and the current state, we can introduce a certain arbitrary nonlinear function that just takes the previous state and the control u as input. And similarly, we can define a nonlinear or an arbitrary observation or sensor function that, given the current state, makes a prediction of our sensor measurement. Then the question is, can we somehow use these nonlinear functions in the Kalman filter as well? And in particular, the question is, or the idea is, can we actually linearize these functions? And then the main idea now is to linearize these functions. And we can do that as follows. So imagine we have this nonlinear function g that we want to use in the Kalman filter. Then we can just say, we can apply a first order Taylor approximation where we linearize at our current pose estimate mu at time step t minus 1. And then we add the derivative of g with respect to the current state times the distance of the current state from our linearization point mu. And this derivative here is also called the Jacobian, and it is a matrix. So remember, G already gives us a vector typically if our state is multidimensional, and now we differentiate that with respect to the state again. And so we end up with an n by n matrix that we can multiply with the distance from our linearization point to get this first order Taylor expansion. Good. The same can be done with the observation function. So here again, this h refers to a nonlinear function that we can approximate by taking the function value at our linearization point mu bar, and then we add the product of the derivative of this function h with respect to the state times the difference from our current state minus our linearization point. And this again gives us a Jacobian. Now this is called the observation or the sensor Jacobian h, capital H, that we can multiply with the difference from our current state and our linearization point to obtain the first order Taylor approximation of our nonlinear function. And now we can plug this into the Kalman filter directly. So we have essentially almost the same equations as before, just now we use our nonlinear motion function to determine, for the prediction step, to determine the mu bar. Then we use this Jacobian G to compute our covariance based on the previous covariance, and by adding this normal sensor noise. And then in the correction step, we again use directly our observation function h at our current state estimate to make a prediction of what the sensor probably sees, and then this difference is multiplied by the Kalman gain to update our state estimate and to shrink the covariance then, or to reduce the uncertainty by this sensor update. We use now this matrix H, which is the derivative of our nonlinear sensor function with respect to our current state. Good. So to summarize the video of this video, we've introduced the Kalman filter first for the linear case, and then we stated that, of course, most robotics problems, most interesting problems are not linear. So we've shown a way how to linearize then the sensor and the motion model in this case, and how this can then be used in the so-called extended Kalman filter to deal with such nonlinear sensor and motion models. And because this was quite theoretical now, we will show a very nice example in 2D that hopefully sheds some light on the functions, the inner functions of the Kalman filter, and also give you some intuitive understanding of what the individual matrices mean, and in particular how the choice of noise, of these noise variables R and Q, influence the estimate of the Kalman filter.